In 1970, Stephen Hawking noticed that the area of the event horizon of a black hole had a non-decreasing property, meaning that the hole should only get bigger no matter what. He figured this out by considering how light would behave at the event horizon of a black hole. However, this isn't the case because black holes evaporate eventually. But before we get into the details, some definitions. A black hole is a point in space where there is such a high mass density, nothing, not even light, can escape its gravitational pull. The event horizon is a sort of point of no return for a black hole, the point where no light can escape. This is where the black hole starts to look, well, black. At the center of every black hole, there is a singularity, which is essentially a geometric point where all of the mass of the black hole is condensed. Virtual particles are a little bit harder to envision than an event horizon or a literal hole. Sometimes particles burst into existence from seemingly nothing. This is all a part of quantum field theory, which states that particles are neat normal fluctuations in a field. They travel in a relatively predictable path and have relatively predictable properties. Virtual particles are messy fluctuations. Imagine frantically splashing at a pool of water rather than carefully dropping a stone and watching the ripples gently fade outwards. When Hawking was thinking about how black holes must only get bigger, some experts convinced him that they must emit radiation because they are spinning. Hawking worked out the math and found that radiation from black holes wasn't from the spin of the black hole, and he wanted to figure out why. Everywhere in space, particles are being created in pairs. They are virtual particles. The fact that they're created in pairs is crucial because the pairs are a set of a particle and its antiparticle, like an electron or a positron. A positron is a particle that has the same mass as an electron but with a positive charge. When these particles are created right next to each other, they immediately interact and annihilate each other. When these particles are created on or near the event horizon of a black hole, however, some wacky stuff goes down. The gravitational field of the black hole can rip one of the particles away from the other, causing one to fall into the hole and one to be emitted as radiation. Then, they don't have the opportunity to annihilate each other. When antiparticles fall into the black hole, they meet their particle pairs and annihilate those particles upon contact. The other particles are pushed away from the event horizon, which presents itself as radiation. So there you have it. Radiation is emitted from black holes even if they aren't spinning because virtual particles are created on the event horizon and they're forced to stay in existence by the gravitational pull of the black hole. Hawking radiation can help us understand the dynamics of a black hole. Despite a universal rule that you can't know much about what's going on beyond the event horizon, it may give us insight into what's going on in there. As Hawking would say, black holes ain't so black.